Hey there, STAT216 students. I'm here to give you a quick supplementary recording about conditional probability and independent events. So, without further ado, how about we dig right in? Conditional probability is a topic that can be simultaneously both confusing and intuitive, and I think the following two examples give us a pretty clear idea for why that might be the case. So, in the first example, suppose you're drawing two cards from a well-shuffled deck. Say you draw an ace first, you can ask what is the probability that the second card is also an ace? And many of you can do this in your head quite quickly. There are 3 aces remaining, and there are 51 cards left in the deck, so the probability of drawing an ace second, given that you drew an ace first, is 3 out of 51. Now, on the other hand, we could ask a slightly different question. Say we roll 2 die, and we know that the sum of the result is a 5. What is the probability that at least one of the die shows a 2? So in this first case, we were very easily able to write down this probability, but in this case, we don't really have any tools at our disposal, at least initially, to try to answer this question. What we'll see is that we actually have all these tools at our disposal already. So what's the deal? Well, intuitively, conditional probability gives us a way to update probabilities when we learn new information. And we saw this in our first example. So what did we do? We learned that we had that we pulled one ace out of the deck. That changes the probability of drawing an ace on our second pull. And many times we'll represent situations like this with a probability tree where you say, okay, ace first, ace second, ace first or not ace, then ace first, ace second. So we'd have our event A complement, B complement, B complement. If the probability of drawing an ace first is 4 out of 52. The probability of not drawing an ace first is 48 out of 52. And here's the 3 over 51 that we saw before, and this will be 48 over 51. And if we don't draw an ace first, the probability of drawing an ace second is 4 over 51, and we have 47 over 51 here. All of these probabilities on this side, or on the second level of this tree, are conditional probabilities. And how do we see that? Well, the probability of drawing an ace second changes depending on whether or not you drew an ace first. Now, in the second example, if the sum of your 2 die is a 5, what is the probability that one of the die shows a 2? There's not an easy way to draw a probability tree for this. We could do it, but it would take a little bit of doing. So what we want to notice is that there's no easy way to draw a probability tree where we have sum of 5, not sum of 5, at least 1, 2, not 1, 2, at least 1, 2, not 1, 2. There's not really a good way to do this. So we needed to develop another trick to be able to, or some more tools to be able to answer this question. And we'll resort to theory to develop a formula to try to answer this question. So if we have two events associated to some random process, we'll call them A and B, the probability of A occurring, given that B has already occurred, is denoted in this way. So this is the probability of A given that B has occurred. And what it is the probability that both A and B both occur divided by the probability that B does occur. Okay, now this might seem a little strange and it's kind of a mouthful, but it has a very intuitive explanation for it. So if we think of these two events as living in the sample space of some probability experiment, say we have A and our event B here, what we're trying to do is figure out the probability of A, or we're trying to figure out if the probability of A changes if we know that B has already occurred. Well, if we know that B has already occurred, what that means is that the sample space that we're interested in is now just the B circle. So I'll shade this in blue, or hash mark this in blue, to indicate that that is the new sample space. So all we know is that B has occurred, but that restricts the sample space to this circle here. Now, what we're interested in is the probability of A knowing that B has already occurred. So where does that put us? Well, if we want to investigate where A occurs, knowing that B has already occurred, it's the middle part of the Venn diagram, the intersection between A and B. If I shade it in red, it'll look like this. And now if we think about how we would calculate this using regular old probability formulas, if we had a number associated to B, or if we could count the number of elements in B, what we'd do is we'd say, okay, the number of elements in B is the denominator, and the number of elements in this red shaded area is the numerator of our probability calculation. That's in essence what this formula is telling us. We want to look at the probability of A and B both occurring divided by the probability of B occurring. This is called a conditional probability because we're investigating the probability of A under the assumption that B has already occurred. And this will be our tool for looking at this second, or the example 2 from before, and we'll go into that in just a second. But before we go into that further, we want to make a distinction between conditional versus joint probabilities. Sorry, there's a typo in there. That should be a joint probability. So joint probabilities are, well, the probability of A and B both occurring, while a conditional probability is the probability of some event occurring given that another event has already occurred. It looks like a straightforward distinction, and it often is a straightforward distinction if you write this down mathematically, but it ends up being kind of confusing when you encounter these out in the wild, when you see probability questions phrased in plain English. So, for example, imagine that we're randomly selecting a registered voter from Flathead County, and we're recording their political affiliation and their stance on abortion. The first thing we could ask is, well, what is the probability that the voter is a Republican who opposes abortion? A second question we could ask is, what is the probability that a Republican voter opposes abortion? Now, these sound very, very similar, but one of them is a joint probability and one of them is a conditional probability. And how can we ID which is which? Well, if we define A to be the event where the registered voter is a Republican, and we define B to be the event opposes abortion, now what we want to do is look at these and try to distinguish which is the joint probability and which is the conditional probability. And the key is to recognize when we're assuming that something has already occurred. And if we look carefully at this second one here, we notice that we want to find the probability that a Republican voter opposes abortion. That means that we're assuming that the voter that we're looking at is already a Republican. So this example is the probability of someone opposing abortion given that they're a Republican. On the other hand, what is the probability that the voter is a Republican who opposes abortion? This is like saying, okay, the person is a Republican and they oppose abortion. So this question is asking us to identify the probability of A and B both occurring. Keep that in mind. It can sometimes be difficult to distinguish between conditional and joint probabilities when they're presented in plain English. All right, let's go back to the die example. We want to roll 2 die. We want to find the probability that at least one die shows a 2, given that the result, or the sum of the result, is a 5. Now, let's label some events here. So we have our event A. This will be a roll a sum of 5. We want the event B, where we have at least one die showing a 2. And the probability that we're interested in calculating is the probability of B, the probability of at least one of the dice showing a 2, assuming that we already rolled a sum of 5. Now, using the formula for conditional probability, we recognize that we need the probability of B and A both occurring, and we need to divide it by the probability of A in this case, because we're assuming that A has already occurred here. Okay, so those are the probabilities we need to calculate to answer this question, but how do we actually get at these? So let's keep this up here. Well, the sample space for our experiment can be organized in a nice way. So if you roll 2 die, you can imagine that one of them is red and one of them is white. So then you want to record the white result and the red result. If we do that, you could get a white 1 and a red 1, a white 1, red 2, etc. down to 1, 6. So then you could get a 2, 1, a 2, 2, down to a 2, 6. Then you could get all the way down to a 6 on your first die, a 1 on your second, 6, 2, all the way down to 6, 6. Great. Well, the number of elements in our sample space ends up being 36. How do you see that? There are 6 rows or 6 columns and 6 rows in this little organization of our sample space. So there's 6 outcomes for the first die, 6 outcomes for the second die. They don't interact, so there's 6 times 6 or 36 total possible outcomes. Now, what is the probability of B and A occurring? Now, what does that mean? That means we roll a sum of 5 and at least one die showing a 2. So the event B and A, if we write it off to the side here, if we have a sum of 5 and at least one 2, then we have a 2 and a 3, or we could have a 3 and a 2. So that means that the probability of B and A both occurring is 2 out of 36. Great, going back up here, we have 2 out of 36. Now we want to find the probability of A. So we want to find the probability of rolling a sum of 5. So the probability of A, well, we could write down our event. You could have 1, 4, 2, 3, 3, 2, 4, 1. And is that it? It ends up being the case that that is it. So what is the probability of A? It's actually 4 out of 36. So the probability of B given A is 2/36 out of 4/36. So if we know that the sum is 5, the denominator becomes a 4 over 36. And what does this simplify to? Well, 0.5. So if you know that the sum of your 2 die is 5, then the probability of at least one die showing a 2 is actually 0.5. Fantastic. For comparison's sake here, what is the probability of at least one 2? So we just want to look at the probability of B here in comparison. So what is the probability of at least one die showing a 2? Well, your first die can show a 2. There are 6 ways for that to happen. Your second die can show a 2. There are 6 ways for that to happen. We overcounted the situation where they both show a 2. So the probability of B alone, or the probability of seeing at least one 2, is 11 out of 36. So we can really see here that knowing that the sum of the 2 die is a 5 updates the probability from 11/36, which is a little less than a third, to 0.5. So it increases the probability, knowing that we have a sum of 5. This brings up an important idea, and that is the notion of independent events. So intuitively, we say a pair of events, A and B, are independent if the occurrence of A does not influence the occurrence of B. And now, if a pair of events is not independent, we say that they are dependent. If we want to formalize this mathematically, what that means is that if we know that B occurs, i.e., if we're investigating the probability of A given B, if they're independent, it shouldn't affect the probability of A occurring. So the occurrence of B has no influence on the probability of A. And similarly, we want the occurrence of A not to have any influence over the probability of B. So we say that the probability of B given A is the probability of B. So for an example, drawing an ace on your first and second pole are dependent events. We saw that the probability of an ace on your second pole depends on the probability of an ace on your first pole. As an example of independent events, if you flip a coin twice, the outcomes of each flip are independent. And we feel that intuitively. There's no dependency. If I get heads on the first flip, there's no reason that that should change the probability that I get heads on the second flip. Now, going back to the example that we just looked at, remember we had these two events, at least one die shows a 2, and the sum of the result is 5. Are these independent events? So what we need to check is if we call the first event B, I think that's consistent. Nope. If we call this guy A and this guy B, what we want to know is the probability of B given A equal to the probability of B. And what we saw from before, the probability of at least one die showing a 2, given that the sum of the two die was 5, was 0.5, but the probability of at least one die showing a 2 was actually 11/36. Now, are these guys equal? They are not. So what does that mean? It means that A and B are dependent events. All right, I hope that cleared up any confusion or potential conflicts of interest that you guys had. Conflicts of interest doesn't really make sense. I hope that cleared up any confusion that you guys had. Stay tuned for a few more examples to help clarify some other ideas in the realm of probability.